So as you see here, the overall plan is today we are going to talk about speed, and assuming that there is interest and we continue the lectures, we'll have then a lecture 2 about mathematical induction and conics, lecture 3 about prime numbers, and lecture 4 just a series of portraits of women mathematicians, biographies and their achievements. About the slides, as usual, for those who already listened to me, I'm making the slides a little too wordy, but the idea is to help me remember things, and also in case somebody ever wants to look at them again, they can look at them with some use. The plan for today, we will start by talking about what is really speed. How do we understand speed? And the final answer will come from calculus. We need calculus to properly define and understand speed. Speed is a derivative of a function. Before reaching that point, we will look at the history. We will go through antiquity and then to Renaissance and see how people talked about speed. Then I will want to define in a very rudimentary way speed using calculus. For that we will need a few notions. I will try to make that as painless as I can. And then after we did that, I will talk about the amazing history of calculus, which started in around the 1700s and developed enormously today. So, to get started, when we talk about speed in everyday use, we just know what we are talking about. We say that car is moving fast, or that man is moving too slowly, and we have the feeling that we know what we are talking about. Sometimes we use speed and velocity interchangeably. For physicists, there are two different notions. Velocity contains not for physicists, not only how fast something moves, but also the direction, while speed refers only to how fast. So we won't, if I use them interchangeably, I will always use it in our common language sense. Now, the moment I talk about speed, what are we really talking about? The average speed over a period of time, or instantaneous speed, or something else? So when you say that car is moving fast, what does that really mean? That if it continued moving at that rate, it would reach a destination very soon, or that at this moment it's moving too fast. So this is what we will try to clarify. Generally, when we say speed, we think of instantaneous speed, although we don't really know what it means and how to define it. So intuitively, speed is a measure of how much distance we covered in a given interval of time. When we say this car goes with 65 miles per hour, it means that if it continued exactly as it's moving now, it will cover 65 miles in an hour. That's very good for average speed, but that doesn't tell us very much about speed at a given moment. And that's what we would like to do. For that, you might say that, well, let's just make the interval not a full hour, but make it just half an hour, or even less, just 5 minutes, or 1 minute, or even a matter of seconds. But then, if we try to do that, yes, then the speed becomes more accurate, except suddenly we don't know what we are talking about. The movement in such a short interval of time is approaching zero, and the interval itself is approaching zero. So there is something unclear about it, the notion of instantaneous speed. The speed must have been around people thinking probably from prehistoric times. I mean, I'm sure our ancestors who hunted animals, knew that they had to run faster than the animal they had to catch or kill. And then when the scientists, people organized into states and had scientists and astronomers and mathematicians, then of course they started observing the planets and the stars moving, and they noticed that they move at different speed, and they wanted to understand why and how come and how to characterize this. So we know that astronomical observations were done already by the Babylonians and by the Egyptians in antiquity, and their observations were quite rigorous and precise. And yet, and we are sure they used references to speed, and yet we don't know what they really understood when they said speed. The earliest explicit references to speed that we know of are from Greek antiquity. So I have to say, I learned many of these things. I had a vague notion of things, but many of the details I learned as I was preparing these lectures. I don't know much of history, but I looked up as much as I could on the internet, in books and web pages, and I found that there were several scientists, philosophers they were called. Everybody who was doing any science was a philosopher. And I found 3 people worth mentioning: Eudoxus, Aristotle, and Hipparchus. And they mention speed explicitly, even though they did not define it. And I will talk a little bit about each of them. So I just have here an aside. I am just thinking aloud of how come, before preparing these lectures, I didn't hear much about Eudoxus and about Hipparchus. And yet, now that I looked at them, they look so important. Aristotle, of course, we all heard about. So it seems that some, just like with the big stars in today's life, musicians and painters, some become big stars and become famous, known by everybody, while others may be doing equally valuable work, and just for some reason that I don't understand, they don't become famous. So back to Eudoxus. He lived in this city, which was called Cnidus, at around 400 BC. That city doesn't exist anymore. Today, it's very close to modern-day town Dacia in Turkey, and the Cnidos is a famous archaeological site near Dacia. If you happen to, Dacia is in a remote part of Turkey, but if you happen to travel there, then for sure everybody will recommend that you have to go and visit the archaeological site. Eudoxus pioneered some very important concepts and methods in mathematics while mostly studying astronomy. So he improved on many of Pythagoras' concepts, and his work influenced Archimedes and Euclid. Some of his ideas foreshadow ideas which appear much later in 17th and 18th century in calculus. From the several treatises Eudoxus wrote in astronomy, I mention one which is called Unspeed. So clearly he was talking about speeds. He was meaning the speed of motion of planets. And he tried, we know about it, the work is lost, but we know about it from Aristotle, who quotes it in his book on metaphysics. And what the ancients were trying to do, they noticed that the planets move in something that on orbits that look very much like circles, and yet there are deviations from circles all the time. And they tried to build a model that would explain. They took it for granted that everything moves around the Earth in a circle, but still it's very strange that there are variations. And so they tried to account, to give a model for how this is happening. So Eudoxus described a geometric model of 27 spheres on which the sun, the moon, the stars, and the planets were moving. And somehow, sometimes when we got to an intersection of two spheres, they somehow moved from one sphere to another sphere, and that explained these deviations. At that, for the observations they could do in those times, this was in 4th century BC, this was quite an amazing theory. We know that it's incorrect. Today we know that planets and generally movement of astronomical objects happens on elliptic or some other, could be not necessarily elliptic, could be, depends on other things. A comet may not be moving on an ellipse, and could be around the sun or around the Earth or around other planets, but in principle most of these orbits are elliptical. And it was the 17th century Kepler who first stated that orbits of the planets were ellipses around the sun. He was the first to state that fact. Until then, Eudoxus's model with modifications was still the one people believed. So I want to talk now of Aristotle, and I'm trying to hide. I don't see the titles. Do you see the titles of the slides? I don't see the title of my slides.
Yeah, you can see it.
Okay. I have a bar from Zoom that is covering it. So Aristotle was such a great person, and he wrote so much that I cannot do justice to him in just a few slides here. He wrote, it is believed, I read someplace that he wrote about 200 books. I'm rearranging my window. He wrote about 200 books, which is amazing. That means that I don't know exactly how long he lived, but it means that he was writing several books a year. I think I went ahead. He established a school which was called the Lyceum, and he prepared, some of his writings were just textbooks for teaching in that school. Others were intended for what we would call publication. There was no publication then, but the books were made public and they were copied, and people shared them. Aristotle had such a profound influence in so many fields of science and philosophy that his works are studied even to this day. So I have an aside here, just mentioning my son, who majored in philosophy. And he actually wrote a very nice thesis for graduation in which he compared Aristotle's and Rawls's ideas about justice and government. So I'm bragging a little bit with my son, but I also want to emphasize that Aristotle's influence and writings are relevant even today. So many of his theories, of Aristotle's theories, turned out to be wrong. The later scientists studied what he wrote and realized that, so for instance, this book Physics, where speed is mentioned, is simply wrong. But Galileo did his amazing discoveries by studying Aristotle's books on physics. And then he realized that Aristotle is wrong, and he wrote books in which he corrected Aristotle's errors. Other things, like in philosophy, it's less difficult, it's more difficult to say that something is wrong. So there are discussions, but the discussions are still going on. So going back to Aristotle, he classified motion as violent or unnatural, like when you hit an object with a hammer or you are throwing an object, and natural, when you just let an object fall. He considered that natural. And he considered there are different laws governing these two motions. And the law of speed, he thought, was that force equals mass times velocity. So the velocity and the force depend on each other, and of course mass plays a role. So if you hit something with a hammer, how fast it will start moving depends on its mass and on the force with which it was hit. For Aristotle's time, this is an amazing statement. It's incorrect. Today we know it's incorrect, but it's amazing that he made this observation and he stated a law. The fact that he stated a law of motion in itself is amazing. The implied equation for the natural motion, for when things fall, is that velocity equals the weight divided by the density of the medium in which it is falling, air or water or some other liquid. We know that this is incorrect as well today, but again, it's an amazing fact that he stated this. By the way, from this, Aristotle concluded logically that void is impossible, that void doesn't exist, because he said if void existed, this density at the denominator would be zero, which would mean that the velocity is infinite. And there is no infinite velocity. Nothing is infinite on Earth. So he said that vacuum cannot exist. So it's an incorrect conclusion from an incorrect premise. It was Galileo who contradicted Aristotle almost 2,000 years later, in the 17th century, and he stated that velocity is independent of the weight. This was very nicely verified in the 20th century by the astronauts who landed on Moon, where there is no density, there is no air, so no density of the medium. So independent of weight, I will show you the video in a few seconds. Whether you drop a feather or you drop a hammer on the Moon, they should drop with the same speed. On Earth, they fall at different speeds because air plays the medium plays such an important role. So I will show you the video now. Let's see if oh, I think I have to share. No, that's not what I want. Can you see this window? You can. Let me share it. Can you see the fuzzy window which appeared in the browser?
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch
You hear the
this.
sound,
I
but you don't
have a
see
good
the
picture
video.
there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. And I guess
You don't see the video? Let me try to.
Yeah. I think there is a button somewhere that one, and I don't know where it is, that allows that to be shown, but it's somewhere in one of the controls.
Here. Do you see it now?
Yes, yes.
Okay, let me restart it from the beginning. So this is a video of the landing on the moon.
Copied both solar wind and penetrometer drum in the ETB.
not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. You have a good picture there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So this demonstrates, it's an experiment showing that Galileo was indeed correct. The weight makes no difference. The speed with which the feather and the hammer are falling is the same. If there is no air resistance, then it's the same speed. The fact that Aristotle was wrong in some of his statements in physics does not diminish his achievements at all. He did the best he could with the observations and tools he had. He established what's important, it's not so much that he established scientific facts, but that he established scientific methods. So let us now try, get back to speed, and let's try to, so do you see my slides again?
Not yet.
Not yet. Let me adjust the sharing.
There it is. It's good.
Good. So I think I went a little ahead of myself. I skipped Hipparchus. Hipparchus, who lived a little later, he lived in around 200 in the 2nd century BC, 190 to 120 BC. He was astronomer, mathematician, geographer. Again, very little is known. He's not one of the famous ones, so very little is known about his life. He wrote, we believe from references, he wrote 14 books, and very little of his work survived. He is famous in mathematics for having used trigonometric tables, which for that time, it was very advanced trigonometry. trigonometry wasn't invented yet. He is of interest right now to us because he described the motions of the moon and of the sun. And while he tried to describe, at one point, he tried to describe a heliocentric system, but then he rejected it himself. He said that it was too complicated and things didn't quite match. So the view that the Earth remains at the center became accepted till 16th century, and Copernicus stated that no, the sun is at the center.
Disappeared
Yeah, I got a maintenance projects that I'm working on.
in the rain.
So I move on now, and we are trying to define speed for ourselves. We allow a little bit of imprecision. So just, I looked up on what dictionary says. One online dictionary says the rate at which someone or something is able to move. Another dictionary said the rate of motion or quickness of motion. The Encyclopedia Britannica says quantity that designates how fast the point is moving. So they give us a rough idea indeed of what in everyday language we mean by speed, but they don't give a clue about what speed really means. So I would say that the average speed is a number expressing the distance traveled by an object in an interval of time divided by the length of the time in time interval. So that's the average speed over a time interval. And I would say that instantaneous speed, or just speed at a moment in time, is the number expressing the ratio from above divided by the time interval when the motion is constant. The motion doesn't go faster or slower, but that's not a good definition. In the definition, I'm using faster and slower, which are already parts of the speed. So critically speaking, this is not satisfactory. We need something better. Now, I could not find any references on who defined speed for the first time. And even Galileo, who lived between 1564 and 1642, who is credited with having defined speed, with what I would call a good amount of head waving, even his definition is not satisfactory. I would have liked to find a translation of the original work where Galileo defines speed, but I could not. So in any case, I saw it stated in several places that Galileo measured speed by considering the distance covered and the time it takes to move that distance. And he described speed as v, velocity or speed, equals d over t, distance over time. And this is what we use today in schools, in high schools, and even middle schools, in physics classes, if we don't want to get into calculus. And it's a perfect, we can work with this. It's something that's acceptable. Galileo has often been called the father of observational astronomy, or the father of modern physics, or the father of scientific method, because he had this method. He formulated a statement, then he tried experiments to confirm this statement, and the statement was either confirmed or it was disconfirmed. So the method that he used is scientific in nature. He was also a builder of telescopes, and many of his observations on the movements of stars and planets and sun and the moon are from his progress in building telescopes. His observations led him to support Copernicus's view that the Earth was not the center of the universe, rather than the Earth and the planets orbited around the sun, and the Earth itself is rotating, and the moon orbits around the Earth. So it was these great discoveries were done in the 16th century, the great discoveries that for us today are common knowledge. Galileo was a champion of heliocentrism, and for some reason, which is not clear to me, the Catholic Church was very much opposed to this point of view. I don't understand why, because this doesn't contradict the Bible, doesn't contradict religion, creation. I think it was just a matter of taking sides with one ideology or another, and they didn't like the group of people who were taking the heliocentric point of view. So he was certain that he will be convicted of heretical views, and he was forced to abandon this view, not to teach it and not to write about it. However, later, when probably the church authorities thought that he recanted properly, he received a permission to write a book, and it was expected that he will write arguments for and against heliocentrism, concluding that heliocentrism. However, the book.
Hello. Oh, hello. How are you?
One of you is answering a
No.
telephone, which is competing with my speech.
Well, I don't know what it will be in the future. It's Joan Ormondroyd is in charge of the group, and she is not in shape to
I'm trying to mute.
I muted her already. This is Dennis. I muted Judith.
Okay, so I'm returning to our story about Galileo. The book that he wrote, Dialogue Concerning the Two Chief World Systems, was published in 1632, and nowadays we believe that he did not intend any malice, although the book was viewed as making fun of the geocentric view. And he was again tried, found suspect of heresy, forced to recant, and spent the rest of his life under house arrest. Such were the powers of the church authorities in those days. We are interested in Galileo because of his work in physics. In particular, we are talking of speed, so the study of moving objects. And he imagined and carried out experiments relating to falling objects to see how fast they are falling, very much like in the video we just saw. The legend says that he actually climbed the Tower of Pisa, from where he could drop balls of different weights and see how fast they reached the ground, and notice that the balls were falling at the same rate. It's not clear that he really did this, but definitely he did experiments with balls rolling down on inclined planes, and made very precise observations of their speed. So he went even further. He showed that for falling objects, the distance traveled is proportional to the square of the time elapsed. And this is crucial. This is in some sense it's part of Newton's, of one of Newton's laws. Now, with every big statement, we hear people, historians, telling us that these were not the first time that these ideas were formulated, that earlier scholars already before Galileo critiqued Aristotle and tried to put his observations on a solid scientific basis. Still, we give credit to Galileo as being the first to put things on such a solid ground. Now I will want to make a smooth transition. I finished the history part of the first history part. We'll have more history later. But for now, I want to make a smooth transition into calculus, and we'll do that by looking at some of Zeno's paradoxes. And there are several of them. We know about them from Aristotle, who wrote them down in one of his works. And we will look here at the dichotomy paradox. Aristotle stated that which is in locomotion must arrive at the halfway stage before it arrives at the goal. So you need to reach a midpoint before you reach the end. So that makes perfect sense. I don't think anybody would debate that if you go someplace, you first have to reach the midpoint. But strictly speaking, if you follow just thought processes, this leads to a paradox. So let's assume that you have to reach a goal. So first, you have to reach the midpoint to your goal. So your intermediary goal is now to reach this midpoint. But to reach the midpoint, you first have to reach the midpoint to that one, which is at 1/4 of the distance. So that's fine. Then this is your goal for now. But to reach this goal, you have to reach the midpoint, which is at 1/8 of the distance. And this goes on and on to infinity. But according to Aristotle, there are no infinities in real life on Earth. Everything has to be finite. Infinite processes cannot exist. So this is a paradox. That means you will never actually reach your goal because it's an infinite process. On the other hand, you clearly reach your goal. You just go all the way to your goal, and that's it. So that's a paradox. Today, it's hard to see it as a paradox. The explanation is that there is nothing wrong with accepting infinite processes in our everyday life. The other paradox, somewhat similar although different, is of Achilles and the turtle. Achilles was a famous runner. He's a god in Greek mythology who could run very, very fast. And the turtle is notoriously slow. So Aristotle described this paradox of Zeno. He said, in a race, the quickest runner can never overtake the slowest, since the pursuer must first reach the point where the pursued started, so that the slower must always hold a lead. So this just replaces it's essentially the same argument as the midpoint paradox, except that the midpoint is replaced by position. So let me explain. So Achilles, who runs very fast, gives the turtle wants to give a chance to win. So says, you start from 100 yards ahead of me. To start, Achilles says to himself, well, let me just run to where the turtle started from. While he runs very fast to that point, the turtle advanced a little bit. Then Achilles tells himself, aha, I have to reach the next point where the turtle is right now. So he runs there, but by that time, the turtle advanced a little more. And Achilles then says, aha, now I have to reach a new point. And this way he is constantly always behind the turtle, and he will never catch up. And to them, this was to the old Greeks, this was a serious paradox. To us, it's a sort of a nice brain teaser. You can ask a middle school child to tell you, where is your reasoning wrong? How come on the one hand that Achilles will never reach the turtle when it's so obvious that he will reach the turtle and leave it behind? So paradoxes are interesting. Sometimes we have to strain our imagination to understand the paradoxical nature of a conclusion. At other times, we understand it immediately. By contrast, there are other things that we should find paradoxical in life, but it's very easy to accept them. And we just accept them because they sound so natural or because we grew up believing them. And it seems to me, I'm just musing here, that the human brain is very well adapted to accommodating contradictory ideas and paradoxes. So a few words about Zeno. Very little is known about him. He lived between 495 and 430, around those dates, and very little of his writings survived, and we know about his life and about his writings from works from other people in antiquity, from Plato, Aristotle, and Simplicius of Cilicia. His paradoxes were not just games of the mind, like they would be today. They were very serious philosophical points about existence, reality. 9 of Zeno's paradoxes are known today, all from Aristotle's works. Zeno was the first mathematician who implicitly, without making it explicit, but implicitly dealt with the notion of limits and infinity. Because in these paradoxes, this is the essence, that there are finite quantities, infinitely many of them, and they add up to a finite quantity. So in the midpoint paradox, you have 1 mile, half a mile, quarter mile, eighth mile, 16th of a mile, and so on, infinitely many of these distances becoming smaller and smaller and smaller. But when you add them up, they all add up to 1 mile. So it's infinitely many quantities adding up to something finite. That is exactly the notion of a limit. Zeno didn't put it this way, but implicitly this is what it was. So this took me to introduce infinite sequences to you. And I am showing to you first the notation. Usually we write infinite sequences as these are numbers, A1, A2, A3, dot, 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 AN, and so on. So for instance, if I take AN to be 1 over 10 to the n, then the sequence is 1, 1/10, 1 over 100, 1 over 1,000. By the way, 10 to some power means 1 followed by that many zeros. 1 over 10,000, 1 over 100,000, 1 over a million, and so on, written down here. Or we can write it in decimal form as 0.000 something, and so on. So this is a sequence. Now this sequence has a limit. We don't add them up in this case. I'm just listing the sequence, and I ask, what's the limit of what is the limit of 1 over 10 to the n? And you can see, especially from the last statement when I wrote 0.1, 0.01, 0.001, and so on, you see that they are becoming smaller and smaller and smaller and smaller, closer to 0, as never actually being 0, but being as close to 0 as we wish. And so this limit has sequence has limit, this sequence has limit 0. The way we write it in mathematics, we write this limit as n goes to infinity of 1 over 10 to the n equals 0. And the way we read it, the limit of 1 over 10 to the n is 0. Sometimes, instead of writing the word limit, we use these arrows. 1 over 10 to the n tends to 0 as n tends to infinity. So we are already talking of sequences and limits of sequences. This is calculus. Now, I will just give you another example or two just to make the notion a little bit more familiar. Let's consider another sequence. an is 1 over n. If I write it out as a fraction, it is 1 over 2. If I write it out as a sequence, it is 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. This sequence also has a limit, namely 0. And it says the same thing. The numbers, while not becoming 0 themselves, they are getting as close to 0 as we wish. Now, just to show you that not all sequences have limits, I'll show you the sequence an equals n squared, which is 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, or just write it out explicitly 1, 4, 9, 16, 25, 36, and so on. Now, you may say this doesn't have a limit, and that depends on your vocabulary, depends on how you define limits. Mathematicians would say this still has a limit, but the limit is infinity. The numbers are getting as big as we want, arbitrarily big. And the way we write this is that limit of n squared as n goes to infinity is infinity. And I am showing you, I think, here another sequence just to an is n over n plus 1, and I will skip the argument that the limit is 1. And now I show you yet another sequence just to show you that not all sequences have limits. And I am giving here a to the n equals minus 1 to the power n times n over n plus 1. So this is negative 1/2, 2/3, negative 3/4, 4/5, and so on. Things keep going left and right on the number line around 0. And this limit has no limit, because if it did, on the one hand, a subsequent, there are infinitely many numbers approaching 1. There are infinitely many of them approaching -1. So you can't have two limits for one sequence. And so this is an example of sequence without limit. These were very simple examples, and I just mentioned an example that's not so very simple, namely the limit of this quantity. Now this is a magical quantity. On the one hand, 1 plus 1 over n gets extremely close to 1 as n becomes big, because 1 over n goes to 0. So anything goes to 1, raised something, 1 to any power is 1. So you may argue that, yeah, the limit is likely to be 1. On the other hand, this quantity in parentheses is more than 1, and the power keeps getting bigger and bigger and bigger. And so a number raised to a bigger and bigger power tends to infinity. So what is the limit here? Is it 1? It's infinity? It's something in between? Well, it's not so very easy to see, but this limit is not very difficult either. This sequence has a limit, and the limit is a certain number that we call E, the famous number E. E is about 2.7182. This, I don't want to get carried away, but this number E, it is worth at some point making a whole lecture just about this number. It has so many interesting properties, and it's such rich mathematics around it. So now I have to get to functions. And functions, according to Encyclopedia Britannica, is in mathematics an expression, rule, or law that defines a relationship between one variable and another variable. But this is not bad. And let's just try to improve on it a little bit. Before that, I want to make it clear that we talk about functions all the time. In economic theory, some say that the price is a function of supply and demand. So we know what this means, whether we agree or not, that's another story. But we know what's the meaning of the word function. Or the speed of a falling object is a function of its mass, the resistance exercised by the medium, and time elapsed. Okay, again, we know what function means in this sense, intuitively. Now, in mathematics, we want to write this in a more precise way. So, for instance, when I take area of a circle equals pi times r square, where r is the radius, and I say that a is a function of r, because the function is pi r square. Or just a very simple abject function from pre-calculus, f of x equals 2x plus 3. For any value of x, I can calculate f of x. We also write this sometimes as y equals 2x plus 3. So all these are functions. Now, a relevant example for us is the distance function. You are traveling, and you want to record your distance traveled at every moment in time. So that will be a function of time, the distance traveled in terms of time. We could, for a falling object, I just replaced the d by s because it's not a distance, but it's some space traveled. So it's a falling object, s of t, at a given time, it went down a certain amount. So graphs of functions have graphs, and graphs in our life are, we see them all the time, we understand them, they are in newspapers, in books, and so this, for instance, shows a number of COVID cases in the last 14 days in a period of time between, I don't know, I won't bother to actually. It's very clear what this means, right? It's a graph of a function. The function is c equals n of d, where d is the number of days elapsed, and n is the number of cases on each day. And here is an abstract graph of a function. So for a function given by a formula, a graph may look something like this curved line, where a, for a given value a of x, we calculate the value b f of x, and we show this for all points a, and gives us a graph. Now, why did I get into functions? I got into functions because I need to define the limit of a function at a given point. And here is limit of f of x as x goes to a is b. That means that when we take a sequence x of n which approaches a, we calculate f of a n, and that goes to b. This is not the most commonly given definition of limit of the function. In a calculus class, it's correct, nothing wrong with it, but it's not what is given as a first definition. It is the most intuitive, so I took this one. The usual definition is much more complicated, and if you can, it's in this third bullet, which I'm not even attempting to read, but it's correct, I guarantee its correctness, and you can try to ponder over it and see if you can make sense of it. It says exactly what I wrote in the first bullet. So one about my terminology, I use sometimes point or number, and that's the same thing because we are representing numbers on the number line, and the number on the number line is represented by a point. Every point corresponds to a number, and every number corresponds to a point. So now, functions may or may not have a limit at a given point. And that's just a good thing to be aware of. We don't need this notion. And there is also Ricci's notion of continuity of a function. And I will skip that. All I am saying here is that in the physics of everyday life, most things and phenomena are continuous. This continuity happens when something has a sudden change or a position of state, or an explosion may make something discontinuous, but in a normal sequence of events, things are continuous. This is a very beautiful and useful notion, and calculus today wouldn't exist without this. So I couldn't just go by and not even mention it. So let's take a break, maybe 5 minutes. It's 11:01. So at 11:06, I will resume and talk about the rest.
Thank you.
Lois, can you hear me? I've come back on.
I can hear you.
Okay.
I would like to ask the people here a question as to whether they prefer the class on Zoom or going back to the museum. Anybody have something to say about that? No.
Well, Zoom really works for me.
This is Douglas Garcia. I think via Zoom is fine with me, but of course, there's nothing better than being in a lecture room and listening and interacting with everyone. But if it's Zoom, I'll do it Zoom. If it's personal, I'll be there. But so far, it's working well for me.
This is Rick Philman, and I was actually looking forward to attending in person.
Okay.
Yeah, I agree with Rick because it's sort of difficult to interrupt and ask a question over Zoom. And I know Peter likes questions.
Yes, I do.
I made the coat. Is this a problem?
No.
But we can actually do it both in person, and from there we can still project, use Zoom from there. So we can, right? Because there too I have internet. I have internet access, so we can.
I think hybrid is a very good solution because there's a number of people that can't attend in person, and that varies depending upon the day, etc.
Okay. I think there weren't many, but I think that hybrid is what people want. Both Zoom and I think Peter agrees with that. Some teachers do not want it, but most do. So, okay, I just wanted to get a little feeling from this group.
I like Zoom because I can go back and look at something and think about it some more if I didn't understand it the first time.
Uh-huh. Yeah. Well,
if the weather is good, we are comfortable going to the museum, then we can do a hybrid. It will be open, whatever. To me, Lois and Barry are the bosses, whatever they say.
Well, we certainly had a good turnout, and so I think it would probably work going to the museum and doing the hybrid. And we have done some classes that way.
Right.
Okay.
How many people are here? I haven't counted it up.
Well, there's 18 participants, including everybody, including Peter.
That's pretty good, considering that, what, actually 2 people signed up? 3?
Initially.
Yeah, that is that's better than my previous in-person classes where I had about 12 people.
Mm-hmm. Mm-hmm.
It varied, but it was around 12.
Mm-hmm.
Well, we also have a number of people that are outside of Santa Cruz that enjoy the Zoom courses because they may be in Texas or they may be in Hawaii.
Mm-hmm.
So we do have people that belong to Ollie Santa Cruz that are across the country.
Mm-hmm. And I should say that Peter has agreed and is enthusiastic about recording the class. So it's being recorded and you will be able to go back and look at those concepts again.
Also, the slides will be available. I will give the link on the last slide. On the last slide, will say which is the link where how to get that link, where you can actually go to the slides. That's the advantage of making them verbose, that you can go back and read them as if you are reading headlines of an article. So it's 11:06. Let me try to continue now. So I am getting to this crucial notion I wanted to get at, the derivative of a function at a point. And this is where I was driving. To be able to define, I had to define first sequences, then I used sequences to define limits of functions, and now I'm using limits of functions or expressions involving functions to define the notion of derivative of a function. Derivative is in a strictly mathematical sense, so don't think of it in terms of what a derivative would mean in finance or in real life. It's a mathematical term, and we just take it as that. So the derivative of the function f at the point A, and that is denoted f prime of A, is the limit of the expression f of x minus f of A over x minus A. So the limit of this fraction is f prime of A, limit as x goes to A. Now what's curious about this? F of x minus f of A tends to go to 0. And since x approaches A, x minus A also approaches 0. So here we have two quantities which are closer and closer and closer to 0, and yet the proportion has a meaning, a very precise and useful meaning. Just as a notation, this is often denoted by df over dx at A, or dfa over dx, or d over dx at f of A, instead of f prime of A. Both notations are used and acceptable nowadays, today in mathematics. Now, one thing to make clear is that the limit of a function at a point, and the derivative of a function at a point, may or may not exist. And if we think of A as being an arbitrary point, then the derivative, if it exists at every point, the derivative is a function itself. So we might be talking of f prime of x, of derivative at any point x. So the derivative itself is a function. if we don't specify the derivative at a point, which is a number. And we write the derivative of a function as f prime of x, or just f prime, or df over dx. So here I'm just repeating what I already said, that we have a quantity which is practically 0 over 0, which makes no sense, but yet in the limit, it's a useful, valid thing, a number. The notation also carries the name. These quantities df and dx are called infinitesimals or differentials. And that's one reason why calculus sometimes is called differential calculus or infinitesimal calculus. And this comes from the fact that, which I will get to history a little later, calculus was discovered by two people. Leibniz was the one who used and introduced this D notation, the differential notation, while Newton was the one who was talking of infinitesimals. I want to give you the geometric meaning of the derivative, and this is very simple. Now, don't get intimidated by the graph and by the mathematics of it. It's very simple. I have a graph of a function, this curve, repeated twice. On the left, I fixed here the point A, and I take a point X. I show how X moves towards A. So I take this line that goes through the graph, the point on the graph corresponding to X f of X, and the point on the graph corresponding to A f of A. And as X, this is a line crossing the graph at 2 points, but in the limit, this becomes the tangent line. And so the derivative of the function at the point A is really the slope of the tangent line at point A f of A. And this is a very interesting and very useful intuitive and geometric meaning of the derivative at a point. It's the slope of the tangent line. And now we are ready. We did our duty with calculus, and we are ready to define average speed formally, which I already hinted at several times. So the average speed, let d of t be the distance covered by the object from its initial position to the position at time t. So this is d of t. The average speed is d of t divided by t, the distance divided by time. So to give it to this a concrete meaning, you are going on a walk or a hike, but you are clearly not going at a constant speed. Could be that you are stopping to rest, or you are going uphill for a while, or you are going fast at the beginning and then slowing down. So the speed is not constant. And you are still very curious sometimes to know your average speed, that I made a walk of 2 miles today and I did it in half an hour or 40 minutes. And so that's average speed, and it's a useful concept, and we can calculate it easily. And now, here I'm giving it as a formula, distance covered between t0 and t, that's dt minus dt0, length of the time interval from t0 to t, that's t minus t0. And this is the average speed between the two times t0 and t. So all the rest is just text explaining the same thing. I mean, this thing I just stated. Now I want to define the speed at a given moment. So at a given moment, t0. For that, I take a moment in time t, and the moment t0, which I think of as fixed, that's where I want to define the time, the speed at t0. And so I'm taking d of t minus d of t0 over t minus t0. Now this is the average speed between time t and time t0. You can think of t being smaller than t0 or bigger than t0, mathematically makes no difference. And the speed at, here is the formula in this line, speed at t0 is the limit as t goes to t0 of the average speed of d of t minus d of t0 over t minus t0. But if you look at it, this is just the derivative of the function d. So the speed at t0 is really the derivative of the distance function at t0. And this is why I needed all the calculus we went through, just to be able to show that the speed at t0 is really the derivative of the distance function at t0. And now we know precisely what we talk about when we talk about distance at a given time. So we finished the calculus, we finished the specific, serious, rigorous definition of speed. So I am ready to go back and talk about some history of calculus. Now this is
Peter, I have a question on the derivative part.
Yes.
So is it, I've often thought a derivative is basically the rate of change. Is that a correct way to think about it?
Very correct. That's exactly, yes, it is correct. And I'm glad you pointed that out. And here it's the rate of change. So we have the change in distance and the change in time. And the rate is their ratio. And in the limit, that's the rate of change at t0. So it is exactly the same thing. And I think later I will be mentioning that every time in life where we mention rate of change of something, we are really talking of a derivative of something.
Okay, thank you.
So the history is such a big subject. Books have been written on it, so I can't do justice. I will just give a few points of interest. And also what I want to highlight is that calculus itself, we talked about derivative, and there is infinitesimal or differential calculus. There is also something called integral calculus. And that's very interesting because integrals are also part of calculus, and it's calculus viewed from a completely different point of view. And that, in fact, historically, I think integral calculus was implicitly used and discovered before differential calculus. We'll see in a few slides that already the ancient Greeks were using integral calculus without calling it that, but really using it. And so the historical way calculus developed is not at all the way calculus is being taught today. And I think that's good, because the way calculus is being taught today makes sense, and we need to quickly get to talking about interesting things. So the name in the English-speaking world is calculus, but in many other countries, it's called mathematical analysis. In France, it's mathematique, analyse mathématique, and in Romanian, analyza matematică. So I grew up by learning it as mathematical analysis. And it's also called, as I said, infinitesimal calculus. And going back to history, any history of calculus must begin with mentioning Newton and Leibniz. They really invented, or if you want to argue with that, they established calculus, but I think they invented calculus. And there was a very big controversy because they lived at the same time. And today we credit both of them with independently having invented and developed calculus. But in those years, Newton became concerned that Leibniz stole his ideas. Leibniz published a book first, but Newton, we know from his manuscripts that Newton wrote his ideas first. So it's a difference of 2 years, and Newton made his notes available, and he claimed to some people, and he claimed that somehow Leibniz got them. And today we consider that those Newton's claims were unfounded. So Newton derived his results and shared his notes with some members of the Royal Society. He published them later as a method of fluxion or infinitesimals. Leibniz published his book Nova Methodus pro maximis et minimis before Newton. So in that sense, Leibniz was there first. But their discoveries are independent. So they even use different names and different notations. Newton called these fluxions, and Leibniz called them these infinitesimals, differentials. Newton was one of the great mathematicians and physicists of all times. And again, books have been written about Newton, his work, his life, so I'm just mentioning a few simple facts here. In physics, he formulated the principles which are still in use today. At any time, we don't need relativity concepts, and they were the only thing people were using until 20th century, when relativity was discovered by Einstein. It's hard to believe that Newton, the genius, dedicated time and effort to alchemy, to biblical chronology, and theological pursuits. To us, it would seem such a waste of his mental resources. Newton was born in a very modest family and had a difficult childhood. He started distinguishing himself later at school, and then, based on he being such a distinguished student, he was admitted to Trinity College in Cambridge, but first as a student paying his fees by performing valet duties for others. Later, he received a scholarship, and he was then permitted to study for an MA. He obtained his BA in 1765, but the university closed because there was a plague. And so he went home, and at home he continued his studies and his work on his own. And in those 2 years while the plague raged and the university was closed, he developed some of his theories in calculus, in optics, and the laws of gravitation. On return to Cambridge, he was made a Trinity Fellow, and his achievements were recognized, and a few years later he was elected a Fellow of the Royal Society. So he was given honors and credit. He also got into administration. He became a member of Parliament and obtained positions at the Royal Mint, where he was quite active. It wasn't, he actually, I read someplace, tried to catch people who were trying to make fake money. And again, seems such a waste. He could have dedicated all his resources, mental resources, to mathematics and physics. But even this way as it is, he did amazing things. Late in life, he became quite quarrelsome, having disputes with Leibniz, of course, but not only with Leibniz, even with other people who have been his friends. However, his fame at home and abroad, and his honor, the honors he received were undisputed. Now, a few words about Leibniz. Leibniz was what you would call a polymath. His publication and contributions to so many fields. Were to so many fields that it's hard to imagine how that is possible. Mathematics, philosophy, history, theology, law, philology, physics, biology, medicine, geology, psychology, and even in what would be rudimentary computer science. He was also active in politics and in diplomacy. He wasn't rich. He was fluent in several languages. He wasn't rich. He was from an intellectual family, his father having been a professor of philosophy in Leipzig. But he was precocious, and he started developing very early, obtained a degree in law first at age 19. In the next few years, he needed to be active in some practical field, and particularly in diplomacy, because he needed something to live on. And on the side, he studied mathematics and physics. His contribution to calculus are from this period. For many years, his star as a philosophy and scientist was rising and enhancing his eminence in diplomacy and in history and theology. Then the controversy with Newton broke out, and Newton was perceived as the winner, and that damaged Leibniz's reputation. So sponsors started dropping him, and he started having a hard time. Also, he had ideas, some of them were already then sort of naive. He had a very optimistic outlook on life. One of his principles was that God assuredly always chooses the best. So everything on earth can be as good as possible because God made it. Nothing could be better. And Voltaire wrote a book, Candide, a novella, in which he is really ridiculing Leibniz's point of view, philosophical point of view. So some of his supporters died or stopped supporting him, and by the time he died, he was old and died in 1716, he was out of favor. And he was just buried in an unmarked grave, which stayed unmarked for more than 50 years. After 50 years, it was the philosopher Kant who started rereading Leibniz's philosophy and started discovering what valuable ideas he had. And that started a whole wave of re-evaluating Leibniz's work. The German Academy published a series of volumes which contains 57 volumes of his works, with an average of 870 pages per volume. Here is a quotation from Leibniz. I cannot tell you how extraordinarily distracted and spread out I am. I am trying to find various things in the archives. I look at old papers and hunt up unpublished documents. I receive and answer a huge number of letters. At the same time, I have so many mathematical results, philosophical thoughts, and other literary innovations that should not be allowed to vanish that I often do not know where to begin. This he was writing to a friend when in his prime. He was an amazing personality. I very quickly want to mention these two women, Maria Gaetana Agnesi from Italy, I think from Milan, lived in 1718 to 1799, and Émilie du Châtelet, 1706-1749. They were not practicing scientists because they were women. It was impossible in those times for a well, we'll get to that. But they both appreciated the new theory of infinitesimals so much that they both actually translated and rewrote and explained, popularized Newton's book, Principia Philosophica. Agnesi wrote these analytical institutions for the use of Italian youth, which is really a work in 2 volumes, and the second volume simply contains an exposition of integral and differential calculus with examples, with her own explanations, but just making Newton available to the Italian youth. This was written in Italian. Émilie de Châtelet translated Newton's work into French and published it, and with her own comments and annotations. So, just a short return to calculus, just as a review. There are processes which have infinitely many steps, and so they introduce us the notion of limit. There are quantities which are infinitely close to zero, which gave us the notion of infinitesimals. We can divide 2 infinitesimals, like we do to get a rate of change or to get derivatives, and that brings us to the derivatives. And then we can add up infinitely many quantities, like in Zenon's paradoxes, and get again a limit. So as an example, a ball, if you think of it, maybe you didn't stop to think of it, but you can consider, if you wanted to calculate the value of a ball, you could slice it up in very thin slices. Each slice would be a disk. The disks are of different sizes, but each disk, if you just approximate it, you could view it as a cylinder and calculate its volume and add them all up and go to the limit, and you get the limit of the volume of the ball. So I want to, in this vein, to mention Archimedes, because Archimedes was born, he was the one who came up with what we would call today integral calculus. He lived in between 287 and 212 BC, approximately. The legend is that he was caught by a Roman soldier while contemplating a drawing of mathematical problems. He lived in Syracuse. Syracuse was conquered by the Romans, and soldiers were given explicit orders not to harm this man because he's so valuable. But apparently a Roman soldier got very upset that Archimedes didn't follow his orders and just killed him. Could be true, could be just a legend. In any case, Archimedes is known for several things. Archimedes' principle in hydrostatics. There is something called Archimedes' screw, and there is also a legend how he used some parabolic arrangement of mirrors, light wooden ships of the invading Romans from a distance. As a mathematician, he is known for the method of exhaustion, and this is a precursor to integral calculus, and this is what I hinted before, that to calculate the volume of a ball, you slice it up in thin slices, or you consider each slice to be a disk. You can calculate the volume of a disk, and then you put it all together to get the volume of a ball. This is nothing but integral calculus. Same for the area of a segment of a parabola, for which otherwise we don't have an easy, obvious formula. Relatively many of his writings survived. One interesting story is the discovery of the Archimedes' palimpsest, a manuscript discovered in 1906, containing several treatises of Archimedes. So that's what a discovery that must have been when they found this manuscript. In the spirit of history also, I want to mention these 2 Chinese mathematicians, Liu Hui from 3rd century and Zhu Zhongzhi from around 500, 429 to 500, Liu Hui has written these commentaries on this famous book, The 9 Chapters of the Mathematical Art, a book composed sometimes between, it goes into antiquity and we don't know exactly its origin, sometime between 12th and 2nd century BC. But later mathematicians studying it and writing commentaries. Among his achievements, he was talking of negative numbers, he was talking of decimal fractions, he had a proof of what we call today Pythagoras theorem. He was doing things which in Europe appeared much, much later. He had an algorithm for calculating an approximation, a good approximation of pi. He must have been an amazing mathematician. And Zhu Zhongzhi was an astronomer, mathematician, politician, inventor, and writer. He was born into a family of respected scholars. Among his mathematical achievements are carrying on with the ideas of Liu Hui and obtaining even better approximations for pi and computing volume of a sphere, which is a typical problem in integral calculus. He also had computations related to the calendar and to eclipses, to sun or moon eclipses. And let's go now to move to India. In India, there was this Bhaskara or Bhaskara too often called. He lived around the 12th century, and he was called Bhaskara too because there was another mathematician of the same name who lived in the 7th century. So he was one of a long lineage of mathematicians and astronomers. He wrote several works, and he had ideas in differential calculus. He also had results in algebra, trigonometry, and astronomy. And another Indian mathematician, a few centuries later, he was the impulse for a rich mathematical school in Kerala, in state in India, and he laid foundations for the development of calculus. Of course, these were not known to Leibniz and Newton, so we couldn't say that they were inspired by works of these Indian mathematicians. But in some sense, these Indians had it first. Of course, they didn't have it, though, in the same precise way. We can, if we read their works, we can see that, yes, the ideas are there, but they were not stated so explicitly. And now, just for pleasure, I'm mentioning the fundamental theorem of calculus. I kept mentioning integral and derivative calculus, integrals and derivatives. So the definitions of these operations are very different and seemingly unrelated, and they turn out to be very closely related. So the subject of the actual statement of the fundamental theorem of calculus is that they are inverse to each other. Given a function f, we can use integration to compute big F integral of f. And I don't want to get into making this much more precise now. The derivative of big F is f. So in this sense, derivative, the derivation is the inverse process of integration. And the other way as well, if we start with an f and we compute its derivative, small f, and then we compute the integral of small f, then the new function we obtain, g and f, differ just by a constant. And that's an amazing result, that really these two, we call them operators, the differential operator and the integral operator, are really essentially inverse to each other. So since I was talking of history of who was there before Leibniz and Newton, I need to mention a few mathematicians who already had some inkling that something is going on there. And in this 17th century mathematician, Fermat, Pierre Fermat, French, and there was a few English mathematicians, James Gregory, Isaac Barrow, and John Wallis. So talking of Fermat, he was a lawyer actually, and mathematics for him was a hobby. And he did, as a hobby, did amazing discoveries. His work wasn't published in hardly anything in books. He just wrote manuscripts and letters and had those circulated. One of the most famous things today, of which we are still talking, is Fermat's last theorem, which he stated as a note in a margin of a copy of a book by Diophantus that he was reading, made a statement. We shouldn't call it a theorem because he never proved it. At least we don't know of any proof. And the theorem was proved in 1995, finally, after hundreds of mathematicians wrote articles and tried it and made contributions and invented new fields of mathematics that turned out to be useful for proving this. I talked about this in another one of my classes, so I won't want to repeat myself here. I want to mention why is Fermat interesting, because he developed a method called adequality, which used in computing maximums and minimums. Now today we know that maximums and minimums are the points on the graph of a function where the derivative is zero. So in some sense, computing maximums and minimums is related to differential calculus, to computing derivatives. And Fermat understood this. So he, without ever explicitly developing calculus, he developed a method for computing maximums and minimums of functions or of various curves, which were really using ideas from calculus. James Gregory was a mathematician and astronomer. He was at the beginning of a very promising career, but died very young, at age 36. He is known to having been the first to publish a statement and proof of the fundamental theorem of calculus in a rudimentary form, because these have not been formulated yet. Isaac Barrows was a mathematician and theologian. He also died very young, at age 46, apparently due to his opium addiction. He had a brilliant academic career and wrote several books. He is best known today for having improved on James Gregory's proof of the fundamental theorem of calculus, still not in the form that we state today, having Newton's and Leibniz formalism. He was also Newton's professor, and he promoted and helped Newton's career. In 1669, 8 years before his death, so he still had a number of years ahead of him, he resigned his professorship at Cambridge in favor of the young Newton and devoted himself to the study of divinity instead, to make room for Newton. And John Wallis, I mentioned already him once in another lecture, he was quite an interesting personality, was mathematician and clergyman. He initially studied to be, I think, right? I don't know, I may be wrong. I wanted to say that he studied to be a doctor, but I don't see it here. So in any case, he studied not to be a mathematician and devoted himself to mathematics after some time, and he's just out of his own initiative, and his contributions in mathematics were amazing. He did contributions in algebra, geometry, trigonometry, and in precursors of calculus. In another lecture, I called him the inventor of the number line. He was, in one of his books, he was trying to explain negative numbers, which people had a hard time accepting. And to explain it, he just said, all numbers are on a line, and we have 0, and we have negative on the left, and positive on the right. Now, we talked of precursors to calculus, then we talked of Leibniz and Newton. So basically we are done with the history of calculus up to Leibniz and Newton. And just to impress you, I want to say what happened to calculus later. Nowadays, calculus is taught first for defining limits, then for defining derivatives, then for integrals. And there is no mathematician who would get a degree who didn't study calculus. High school, I would say most students have to take some rudimentary calculus. I wish everybody had to take some calculus because it is so important and so rich. After Newton and Leibniz, the pace of discoveries in calculus just accelerated, and there are many names, in particular Euler, Cauchy, Weierstrass, and Riemann. People would probably blame me for mentioning only these 4. Nothing wrong with these 4. What's wrong is how many I leave out. Calculus had an enormous development. Euler was a prolific mathematician, lived in 18th century, studied in Basel, Switzerland, and then in his adult life he was at academies in Berlin and in Moscow. And he wrote so many mathematics, so he did so much mathematics and so many discoveries that it's hard to find a field where Euler's name is not mentioned. His eyesight became very bad already in his 30s, and he became blind in his late 50s, and then he just continued working and dictating his works. He remarked, now I will have fewer distractions. The mathematics was so important for him. This website, there is a website, I won't go there now, but this is dedicated to list of things named after Euler. There are over, now I don't see it here, over 50 things, theorems or constants or things that were his name. Cauchy was a French mathematician, and he's very close to my heart because he practically established the field of complex analysis, and that was my field when I was studying as a beginner. And Cauchy initially trained to become an engineer, but then switched to mathematics. He was a prolific mathematician, publishing about 800 articles and several books on a variety of topics in mathematics and mathematical physics. In 18th century, mathematics was becoming, people were not philosophers anymore, who were just doing mathematics as one of their interests. Mathematics started becoming a field in itself. His importance comes from his insistence that mathematical analysis had to be done rigorously, not as an intuitive extension of algebraic methods. About his life, we wouldn't like him. He was a royalist and very strong feeling Catholic, but he was true to his word. He sacrificed his career and suffered in his life because he acted according to his beliefs. So I wouldn't like him probably as a person, that I would admire and respect him as a professor of mathematics. This mathematician, Karl Theodor Wilhelm Weierstrass, a German mathematician from 19th century, he started his academic career slowly, training for a government position first. Then he became a school teacher, and he taught mathematics, physics, botany, and PE, gymnastics. And finally, after he proved himself in mathematics, he received a position at the university in Berlin. And he made very precise the notions of limits, continuity of function, and studied properties of functions, and brought in many new fields of function theory. One of his great, I shouldn't say achievements, but great things he did for mathematics was his support for Sofia Kovalevskaya, who was an extremely gifted and promising young mathematician. The Berlin University not only refused to accept her as a student, but did not even allow her to attend lectures. So Weierstrass taught her privately the material he was teaching at the university, and Kovalevskaya became a well-known mathematician in spite of the obstacles she faced because of being a woman. And Riemann did so much in such a short time. He died young too, at age 39. He opened new fields in geometry. He put integral calculus on a solid basis. What the integral as taught today in high schools and colleges is the Riemann integral, the way he defined it. And he did things in geometry, in calculus, in complex analysis, and in number theory. And it's hard not to emphasize his greatness as a mathematician. In a very short paper, only 9 pages in 1859, he analyzed a complex function, which today we call the Riemann zeta function. And he established in that paper, in 9 pages, how important this is to studying prime numbers. And made a statement about, actually, he asked as a question a property of this function, which to this day is not known. It's called the Riemann hypothesis. And many mathematicians consider this to be the most important unsolved problem in mathematics. The great mathematician David Hilbert is quoted as having said, "If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven?" Other concepts related to derivatives. Acceleration is the rate of changing speed. So that is a derivative. It is the second derivative of the distance function. Rates in economics, inflation, stock appreciation, depreciation, and other prices. Rates in technology, rotations per minute of an engine, or rates of chemical reaction, rates at which diseases are spreading. All these are rates. They are essentially derivatives of some function, of an appropriately defined function. And if you want to formally study any of these fields, we have to get the appropriate tools from calculus. There is an interesting dichotomy, an interesting split between continuity and discreteness. On the one hand, we want continuity because that tells us more. But on the other hand, when we have too much data in continuity, then we lose the overall view of what's happening. So, for instance, with COVID, we don't want to see the number of COVID cases each day, but we prefer to see an average over 7 days and graph that. So for other things, we want things to be as discrete as possible, as continuous, as possible. For others, we want to induce some discreteness. Now, modern mathematical analysis became a whole field in itself. So there are journals dedicated to analysis, and analysis now contains new fields: complex analysis, differential equations, numerical analysis, which were not part of the original calculus, field of calculus. This statement is undeniably true. Our everyday life would be different if we did not have calculus and mathematical analysis. So, to review, what did we do today? We started by talking about what speed might mean. Then we talked about the history of the notion of speed. We talked a little bit, I hope not too much, about calculus by defining limits of sequences, limits of functions, and derivatives of functions. Then we gave a rigorous definition of speed, and we took a lengthy look at history of calculus, starting with Leibniz and Newton, then going back to the antiquity and going through China and India, and then coming back to Europe to see who came before Leibniz and Newton and what happened after them. And we made then more remarks about where derivatives are useful. For next time, I have two smaller topics. One is mathematical induction, which is a method for proving statements. The other is about conics, which is a class of curves. Here is some food for thought. Probably all of us have been looking at the speedometer of a car. What is the speedometer really showing? Is it the speed over an interval of time? Or is the speed at given, the needle sometimes keeps, or digits keep changing? Is it at any given time, or is it the instantaneous speed? Or is it a smoothed value of the instantaneous speed? Or is it something else? So what does the speedometer really show? You can just ponder on this. Also, what is the mechanical electronic method for obtaining the speed? How do we get in a car? How do we get it? Is something connected to the wheels or to the axle, or how do we get it? And the similar question about the sadder reality of traffic police trying to catch us speeding when they check by radar the speed. What's happening there? How does that little radar device get the speed of the car? How is it happening? So we might just ponder these questions. Now here is, I will make the presentation. This is a folder, the link to a folder. It's quite complicated, and I can't make it simpler. And in this folder, I put all the lectures I presented. So this lecture, I will put it this afternoon in this folder. And if you have, you can either somehow, if you manage to save this link, then you can type it in, or if not, send me an email to my email address, which is much easier to remember. And I will send you the link in a reply. So thank you very much for your attention. And I hope to see you all next week.
Thank you, Peter.
Thank you.
Bye.